Today we're going to do a two-step reaction, starting with benzyl chloride, reacting this to form benzyl cyanide, and then hydrolyzing this to form phenylacetic acid. The first step in this process to form benzyl cyanide is one we've actually done before in the previous video, but this time we're going to try a different procedure to see if we can get a cleaner product. Here's our starting materials for the first step of the reaction sequence. Let's go through these. First up is our benzyl chloride. We're trying the new process out on a small scale, so we've weighed out 4 grams of liquid benzyl chloride. We've prepared this in the previous video from benzyl alcohol, so check it out at the link shown if you want more information. It's a very unpleasant compound, so do minimize your exposure as much as possible. Reacting with this we have our alkali cyanide salt. Here we've weighed out 2.8 grams of mixed sodium-potassium cyanide, which contains these in the 1:2 molar ratio. We prepared this in the previous video using anhydrous potassium ferrocyanide and sodium metal, and dehydrating the aqueous solution using absolute ethanol. Have a look for more details. Alkali cyanides are extremely toxic and will kill you rapidly, so take great care with handling them. Make sure they never come into contact with acidic compounds or deadly hydrogen cyanide gas can be generated. And finally our catalyst for the reaction. This is 0.3 grams of sodium iodide crystals. Our understanding is that potassium iodide unfortunately won't substitute here, but it might be worth a try anyway. We'll perform the reaction in a 100 ml flask which is set up on a hot plate, and you'll need good magnetic stirring to do this properly. Use ventilation as well because you don't want to risk it with alkali cyanide in here and with very unpleasant benzyl chloride as well. Let's get our dry starting materials into the flask first. The sodium iodide. And the sodium-potassium cyanide. And next we'll add the benzyl chloride. As a solvent we're going to use a mixture of 15 ml of acetone and 5 ml of absolute ethanol. First we'll use this to wash the beaker which contains the benzyl chloride. Then we get the rest in. Okay, we're now ready, so first of all let's get the stirring going fairly vigorously. And now we set up for reflux. You'll need to use fairly cool water in the condenser in order to stop the acetone vapor from slowly escaping. Let's get heating the mixture until we've got a gentle reflux. And now we'll keep this going for the next 3 hours. So what's happening in this first reaction step? Well, cyanide ions are very good nucleophiles, and will attack carbon atoms in other compounds where they can displace a good leaving group. In this case we've got benzyl chloride which has a carbon with a chlorine atom bonded to it. The cyanide can attack the carbon and kick out the chlorine atom as a chloride ion. And so we end up creating our product, benzyl cyanide. In doing so we've effectively added an extra carbon atom onto the molecule from the cyanide. The sodium iodide acts as a catalyst because in acetone it's able to form benzyl iodide as an intermediate, and iodide is an even better leaving group than the chloride. The iodide is regenerated in the process. The color and texture of the solid in the flask seems to change over the 3 hours to a more granular and whiter colored solid. We stop heating and stirring and allow the mixture to cool. And now let's filter. We wash the flask and the solids with 10 ml of acetone. So let's transfer the filtrate containing the phenylacetic into a flask. The aroma has changed and there's no more irritating benzoyl chloride present. So now we're going to set up for distillation and remove the solvent from the filtrate. Interestingly, it's quite a pale colored mixture, unlike the orange to dark brown colored mixture you get using the previous method we tried. We've got the solvent distilling off nicely now, and pretty soon it's all off. At the end of the distillation, the yellow oily liquid remains in the flask, with the characteristic slightly poppy aroma of phenylacetic, otherwise known as benzyl cyanide. There's a little bit of water as well, as you can see. Okay, we're going to move right on to the next step of the reaction, which is to hydrolyze this nitrile to the corresponding carboxylic acid. To do this, we're going to use 10 ml of 50% by volume sulfuric acid. We've set the flask back up with a reflux condenser again. So let's add the acid. And closed back up. And now we'll heat and stir the mixture. Hydrolysis of the nitrile to the acid should be pretty rapid. Once the mixture reached reflux temperature, we kept it there for 1 hour. The color of the mixture turned orange as it was heated. You can see that the non-aqueous component is getting darker. So let's leave this for an hour. Let's also have a look at what's happening in this second part of the reaction. Organic nitriles and in fact alkali cyanide salts are easily hydrolyzed both in acidic and alkaline solution. Let's look at the acid hydrolysis that's occurring in this reaction. First of all, the nitrile is protonated, leading to a more electrophilic carbon in the nitrile group. This is then attached by water as the nucleophile. The resulting species fairly easily loses an proton and then rearranges to form an intermediate hydrolysis product, an organic amide. And as you know, amides can also be hydrolyzed in a similar way. The oxygen in the carbonyl group of the amide is protonated, leading to a species which, just like before, ends up getting attacked nucleophilically by a water molecule. The resulting species then eliminates ammonia to form the product, the carboxylic acid. As you can see, the color of our reaction mixture is turning darker. And after an hour of refluxing, it looks like this. So we stop stirring and allow to cool. There's a dark red-brown colored organic layer and a yellow colored aqueous layer. This actually looks very similar to the product you get when you hydrolyze benzyl cyanide made by the other method we tried previously. Okay, this is chilled down now, and the reaction mixture has a very strong sweet acacia honey-like aroma. Phenylacetic acid. So there's definitely some in here. We now need to get it out. So here's 10 grams of solid sodium hydroxide. Enough to completely neutralize all sulfuric acid, and also convert all phenylacetic acid into the sodium salt. We used a couple of ice cubes and a little water to make up a cold solution. Okay, let's add the reaction mixture. Well, if there was a lot of phenylacetic acid in here, we'd get a solid crystallizing out, but it doesn't always happen. Let's check the pH first and make sure that the mixture is strongly alkaline. It is. And what this means is that any phenylacetic acid should be dissolved in our aqueous solution as sodium phenylacetate now. Here's our mixture. It's cleared up a bit, but there's some brown organic impurities floating on the top still. Let's get this into a separating funnel. And now we're going to add 10 ml of dichloromethane to the mixture, which should hopefully dissolve out the organic byproduct materials. Okay, after a good shake, let's see where the brown goes. It's going into the bottom DCM layer, which is good. And our aqueous layer is looking quite clean. So let's drain off the DCM layer. Okay, great. We repeated the process with another 10 ml of DCM just to clean up a bit more. And now all the impurities, starting materials, and brown color is in the DCM extract. Let's separate the aqueous layer now. Okay, well, to get our phenylacetic acid out we'll need to acidify the mixture, so here's about 12 ml of concentrated hydrochloric acid. Let's just confirm the pH of the mixture is now strongly acid. Now we'll get the mixture into a separating funnel. It's murky looking and there are some drops on the surface, so it looks like there's some product in here, but not that much. We'll use a couple of portions of 10 ml of DCM to extract this. We shake vigorously and allow to separate. And now we'll drain off the bottom DCM layer. We repeated the extraction with another 10 ml of DCM. Then dried the combined DCM extract using some anhydrous magnesium sulfate. Okay, let's evaporate the DCM solution down and see what we've got. And here we go. There's some oily residue left in the petri dish, as you can see. And on cooling this crystallizes, forming an off-white solid with a very potent strong petrochemical honey aroma. A bit like a form of artificial fake honey flavoring. Well, we can scrape up some very crude product from here. If we do this, then we've got about half a gram of product. A bit disappointing really. There's not much that can go wrong in the second hydrolysis step, so this means that the product of the first reaction only contained a small amount of phenylacetonitrile, unfortunately. So our recommendation if you want to do this reaction is to use the more classic method of reacting benzyl chloride and sodium cyanide together in a water and ethanol solution. We covered this in the previous video, so take a look. This gives reasonable yields of phenylacetic acid when hydrolyzed. It may also be that we simply didn't reflux the mixture for long enough, but who knows. Another option is to produce mandelic acid and then reduce this, but this is a bit more complex. We also covered this in the previous video, so take a look for more details. Stay tuned for more reactions.